We are now recording. Let's get the slideshow set up for the current slide. Goodness, this takes too long. I can't do this ahead of time because once I do this, I can't get back to launch Screencast-O-Matic. So that's what's awkward about it. I wish I could get this stuff done ahead of time. And I wish I could get this stuff done, but see, this doesn't. You can't see what this would be recording. I can, and it's not the best thing. You can't see anything because I don't have a projector on. But for some reason, that didn't work. So let me try it again. Here's interview. Okay. I guess the button didn't click. Okay, hopefully this time. Yes. All right. First, I want to know, any questions, anything we've done so far? All right. Now, last time, we had started example 3, had read it, revolving around the horizontal axis, find the volume V of the wetting band obtained by rotating the region between the graphs of alpha of x equal, wrong pen. This almost seems senseless to do this, but I'm going to, because as soon as I go to write, it's going to shrink back. Okay. Here's what we got. Find the volume by rotating the region between the graphs of alpha of x equal x squared plus 2. Get my pen activated. Yuck. Go through this so many times. This is such an awkward program. Okay. Oh, that's right. I can't write on this anyway. Here is the f of x equal x squared plus 2, and this is g of x equal 4 minus x squared. That region that's intersected by those two parabolae, that's the part that we're rotating around the x-axis. Okay, so what that means is you've got to determine. Now, did we figure out what the points of intersection were last time? We didn't. I didn't think we did. Okay, you got to figure out who's on first, who's on top here, and they drew the figure for you. Most of the time, you're not going to have this drawn for you. You got to figure it out yourself. Well, an easy way to do this is just to plug some values in. X equals 0, say. X equals 0, this one is 2, this one's 4. So obviously, that one's on top at x equals 0. Okay? Now, if you had chosen x equals 2, then this would have been on top, and that one would have been on the bottom. So you have to know where it is. So actually, before you pick a 0, let's find the points of intersection. Okay? And we didn't do this before? Okay, you know how to do it though, right? That's where the two are equal to each other. And of course, when I go to write, it's going to fall back down. Well, I can't get it to go down. There we go. Okay. I've already got the pen. You say, okay, now it's finally showing up. Okay. I'm going to say alpha of x, x squared plus 2, is equal to g of x. It's g of x, but g of x is 4 minus x squared. Okay? and you solve this for x. So what would you do? Add x squared to both sides, and go on and subtract 4 from both sides. Okay, and what does that give you? 2. This is so bizarre. No. 2x squared minus 2 is equal to 0. Now what? What will you do next? Yeah, factor out a 2. That leaves you x squared minus 1 equals 0. You can divide out that 2 with no loss of generality here because that's an equation. This then gives you x plus 1 times x minus 1 equals 0. And obviously here then x is equal to minus 1, x equal plus 1. So those are your regions that we're going to be integrating from x equals minus 1 to plus 1. Now that you know that, then pick some number in there, like 0 in that region between x equals minus 1 and x equals plus 1, and see who's on top. And sure enough, g of x is on top. Okay? So, what are we going to be doing then? We're rotating not around the x-axis. I thought we were. Oh, a horizontal axis, not the x-axis. Okay? We're to rotate this band, this region, about the horizontal line y is equal to negative 3. And that's why they have this drawn here. It's not just revolving around the x-axis, it's revolving around the line y is equal to negative 3. So what we're revolving, since we're dividing our x's between minus 1 and 1, we're going to be doing a dx. Dx is going to be a delta x in here, very small increment here. So what you're doing is taking the increment a, revolving that around there, and b, revolving that around there. It's this length that you're revolving around there, making the wedding band, okay, about the line y is equal to 3. So here's your top function, this one. Here's the lower function, this one. So it's the top one minus the lower one, okay? But you're revolving those around the y-axis, so the distance you're revolving, your radius here is 4 minus x squared plus 3. 4 minus x squared would just be y is equal to 0, the x-axis. You're doing an additional 3, so it's 4 minus x squared plus 3. That's revolved around there, so that becomes your circumference. So you got the 2 pi r there, minus the b here, which is x squared plus 2, revolved around this, plus 3. Revolve that around there. And so that will give you just this region being revolved around there. This part minus this part, okay? And that's what they're showing here. The g of x plus 3 on top, alpha of x plus 3 on the bottom, that you're revolving around that axis, okay? Those are the inner and outer radii. And then you integrate that from minus 1 to plus 1. So this band here is getting integrated from there to there. So it's an area that you're dealing with, so it will be this is your, why here they call it g of x, here they actually name it. So it seems like to me, let's actually write it in. This is 4 minus x squared plus 3, which you could rewrite that as 7 minus x squared. That's your outer radius, and your inner radius is f of x plus 3, which is x squared plus 2 plus 3, which is x squared plus 5. That's the inner radius. So your integral here that you're integrating from minus 1 to 1, this is the ring. The area that's in there would be, here it is, 7 minus x squared minus, so aggravating, minus x squared plus 5 squared. Your pi's out front, dx here, you're going from minus 1 to 1, okay? Because you're doing the area of this outer circle here, which is that 7 minus pi x squared, okay, pi times that, and minus pi times the interval, that's the one you're subtracting out of there, so that's why you're doing areas, pi r squared, okay? Now, that's to set up the problem, which really probably requires the most thinking and working through. The rest of it's just math, okay? So let's first square those two binomials. Now, I'm running out of room here, so I think I'm going to erase. I thought I was going to erase. Well, it's not giving me an option to wait. Okay. All right, finally. Okay. This program is really, really, really awkward. Okay. Okay. So let's square that first. This is pi, integral from minus 1 to 1. What happens when you square that first binomial? What you get? A little 49 minus, no. Second? Yeah, you got 14x squared. Remember, twice the cross product. Okay, 14x squared plus x to the fourth, because it's minus and minus, that's plus, minus, let's put this one in parentheses. What do you have there? X to the fourth plus 10x squared plus 25 dx. Okay? Now, that's going to be the, goodness gracious, this is so aggravating. Okay. Pi times the integral of minus 1 to 1. I swear. Okay. Let's do the x squareds first. I mean x to the fourth first. This is an x fourth minus an x fourth. Those go away, don't they? Isn't that nice? Okay. Then you have a, let's do the 49 next. 49 minus 25, that would be 24, right? Okay, so that's taking care of those. And then we have a minus 14x squared minus a 10x squared. That would be minus 24x squared dx. All right. What's an obvious thing you can do next? Yeah, factor out a 24, so this would be a 24 pi integral from minus 1 to 1 of 1 minus x squared dx. Okay, I think we can do this integral. This will be 24 pi. Antiderivative of 1 is x, right, minus cubed over 3. Okay? Evaluate that from minus 1 to 1. All right? That'll be 24 pi. And when you plug a 1 in, oh, why didn't I do this earlier? What do you notice we got here? Symmetry. So to make life easier, just do from 0 to 1 and double it. Okay? So if we had done that, that would make this a 48. I swear this thing is so aggravating. I go to erase and nothing happens. Okay. So that makes that a 48, and we'll go from 0 to 1. Alright. That's what doubling that does, and it will go 0 to 1. Oops, I didn't erase that one. Okay. We have 48. Alright, and what do we have here? See why I like to have the 0 in there, it makes it so much easier. This will be 1 minus 1 over 3. 1 minus 1/3 would be 2/3, right? The 0, take care of that, it's out of there. So this will be 48 pi times 2/3. Now, 3 will go into 48. 16. So this is 32 pi. All right. Yep, that's what they got, 32 pi.
Could you explain how did you get x minus, 7 minus x squared?
Square it?
Yeah.
Yeah. Explain how you square that.
Yeah, how did you get that?
How do you get 49 minus 14 x squared?
Previous one.
Oh, how do you get this?
Yes, sir.
Oh, okay, got it. Okay. What we're doing is taking the dx here from minus 1 to 1. So you got that part. Okay. And it's the area of, when you do the dx, you're only doing this little line from B to A. Okay? Rotate it around there. And that's what they did. They took this one and rotated it around the line y equal -3. So basically, you're looking at an area now. The integral is going to make it a solid. But right now it's an area. And it's the area of this outer ring, that's gx plus 3. So the g of x is, I already erased this, that was the 4 minus x squared plus 3 would be 7 minus x squared. Okay? That's the radius that you're going around here. So basically you have a disk there of radius 7 minus x squared. That would be 4 minus x squared, that's the g of x, plus 3. And 4 plus 3 is 7 minus x squared. That's the radius. Now, the area of that disk is pi, there's your pi, times the radius squared. That's your radius squared. And then times your dx would then be the thickness, and if you integrate from here to here, you get the whole volume. Okay. Minus, though, you subtract out this inner radius here, and that came from this one, which was alpha of x, this alpha of x, x squared plus 2 plus 3. So that's your x squared plus 5. That's that one. And you're subtracting that area away. Well, that is pi times this radius, x squared plus 5 squared times the dx. Okay. So, yeah, you're doing the outer area minus the inner area. The outer area is pi times the outer radius squared. The inner area is pi times the inner radius squared. So basically, your pi comes out of both of them, and the minus just is the outer area minus the inner area. And that gives you that band, and you integrate that band from -1 to 1 x. You got it. Does that answer it? Okay. All right. Now, my head's clogging up on me. Sorry about that. All right. Moving on to example 4, which I think is this next figure here. I don't know why. What I'm doing, that's not the best way to do this, but this. All right. Example 4 says, find the volume obtained by rotating graphs of f of x equal 9 minus x squared. That's this f of x here, that blue curve there. And y is equal to 12. That's the upper line there. Okay. About, for x equals 0 to 3, here's x equals 0 to x equals 3, so it's that. About, first it says the line y is equal to 12, and then later you're going to do it y is equal to 15. Okay, well the line y is equal to 12 is going to give us a solid shape here. Okay, here's the f of x equal 9 minus x squared. Here is y is equal to 12. Yeah. And then you're rotating that about y is equal to 12. So you're rotating this, and it happens to come out because this is 3 here, that's 3 there, to be there. So it looks like a megaphone pattern, solid megaphone road. That's what they're showing here. Okay. And because that is solid, this is rotating about itself, the y equals 12 axis here. Then you're going to have the outer radius, which is now b. Okay. Outer radius is, you got to say a minus b. Okay. A is 12 minus b is 9 minus x squared. So 12 minus 9 would be 3. Minus a minus x squared is 3 plus x squared. So that's what you're rotating. That's your outer radius. Okay? And that's now a disk. Okay? It is a disk. The radius is 12 minus this. Okay? And then you're going to square that. 12 minus this would be 3 plus x squared minus minus a minus is going to be, make that a plus. 3 plus x squared. That's what you're rotating about the line. So that's going around there from 0 to 3. Okay? So, of course, when I go to write this, it's going to shrink. Okay. I don't know what that line is. I'm going to see if I can erase it. Yeah. Okay. Okay. Now, one thing to point out to you, if you're drawing this yourself, it's probably not going to look like this because you're probably going to draw even scale. This is 9 on this scale. That's 3 on this scale. So your X is really expanded and your 9, your Y's are really compressed. So yours won't look just like this probably. Mine wouldn't for sure, unless you scaled it exactly the same way. Okay? So what we've got is the area, and this is a disk, and you're doing a dx here. So the x is going from 0 to 3, because they told you that. Pi is out front. R squared, excuse me, is 12 minus, I said it wrong, I think. Yeah, no, I did. 12 minus a 9 minus x squared. So that would be 3 plus x squared, pi r squared. And then your dx is going to give you your distance there, okay? So what would this be? Pi times the integral from 0 to 3 of 9 plus, okay, I couldn't, 6, yeah, 6x squared plus x to the 4th dx, okay? And what's the antiderivative of that? 9x plus 2x cubed would have been over 3. 6x cubed over 3 would be 2x cubed plus x to the 5 over 5. Okay? And we're evaluating that from 0 to 3. It's going to be a little messy on the 3 end, but let's see what we get. That would be pi times, okay, the 3 part's not too bad. Plug in a 3, 9 times 3 is 27, plus 2 times what's 3 cubed, 27. 2 times 27 is 54, plus, all right, 3 to the 5th power. A little louder. 242? 243? Okay, let me, yeah, that sounds reasonable. Over 5. Now, when you do the lower limit, all the zeros contribute nothing. So, what we have here, running out of room to write it. I think I'll write it over. No, I can't write it here. For some reason, it won't let me write there. Pi times, I'm sorry. I worked out in the yard, both, you know, a lot of Saturday and a little bit yesterday afternoon. And I think I've gotten all clogged up. I don't know, but it's just hard to breathe. 5 will go into this 48 3/5. Okay. Well, 48 and 54 is 112 plus 27 is 337, I think. Let's see. I'm sorry. I was reading 243 again. sorry, 48 and 54 is 102, and 27 is 129 and 3/5. And they probably write it as a fraction, so that would be 45 and 3 is 48. 14. Yuck! This thing is so aggravating. And then 648 over 5 pi. That's what I got. I don't know if they, is that what they got? 648 over 5 pi. Okay? That's the first. Sorry. I'm having trouble breathing. It's aggravating. All right, that's the first one. The B part says, don't rotate it about the line y is equal to 12, but rotate it about the line y is equal to 15. Okay? So in this case, you've got that same strip that you're rotating, but it's not rotating into a disk, it's rotating into a washer. Okay? Your outer radius is going to be, just as we had before, well, not just as we had before, it's 15 minus 9 minus y squared. So 15 minus 9 would be 6 plus x squared. So the outer radius is 6 plus x squared. They'd write it this way. I'm writing it 6 plus x squared. Okay, that's 15 minus 9 is 6 plus x squared. And the inner radius is just 3. Okay? It's from 15 to 12. So it's 3 squared. 3 is the radius, and then you square that. So that, yeah, that's where they get the 3 here. Okay? Now, what we have here, I like to think of this as a Christmas tree stand. For a very skinny Christmas tree, you flip it over and that's down the middle there. All right. So there are your 2 radii. Your volume calculations, pi, again, you're going from 0 to 3. Now your outer radius is 6 plus x squared minus the inner radius is just 3 squared, which is 9 dx. Okay, so that's going to be pi integral from 0 to 3. What's 6 plus x squared squared? So again, 36 plus 12x squared plus x to the 4th minus 9. Well, 9 from 36 will be 27, right? dx. All right? So doing the antiderivative of that, pi, that'll be what? 27x plus, what did you say, 4x cubed, that's right, over 5. Okay, evaluate that from 0 to 3. All right, the 0 I can do, but the 3 part is going to take a little more work. That would be 81. 27 times 3 is 81, plus 27 times 4. Seven times 108. Okay. And then 3 to the fifth is what? 243 fifths, which is exactly what we had over here, 243 fifths, which we had as 48 and 3/5, I believe it was. Oh, there we go. 48 and 3/5. Okay. Yuck. Why does it keep doing that? Okay. Whew. Pi. Now, let's add those together. That's 189 plus 48 is 237 3/5, I believe it is. 237 3/5, which would be 35 and 3 is 38. 15 and 3 is 18. 10. Goodness gracious. My head's clogging up so badly I can't think. 38, 15 and 3 at 18, that'd be 11. Okay, pi. I hope that's what they got, because I sure don't want to have to think, yeah, 11/88 fifths pi. Okay. There's nothing. The hardest part is the fractions, the math part. The calculus is really the easy part. Setting it up takes a little bit of effort, okay? But actually doing the integrations is almost the easiest part of it. It's just then adding the fractional values. Now, so much for that. Now they've been trying to get to this thing all along. Let me blow it up just for the time being. We're going to get right back down after this. What we have here is revolving around a vertical axis. Revolve the volume of a solid obtained by rotating the region under the graph of f of x equal to 9 minus x squared. That's what's shown there, right here. Y is equal to 9 minus x squared. For 0 less than or equal to x, less than or equal to 3. So you got 0 to 3 here. Okay. About the vertical axis, x equal -2. Here's your axis. All right. Now, there's two ways to do this. They're going to show you this way first, because that's the only one we've talked about. In the next section, we're going to do the second way. We'll probably come back and do this very same problem here. Okay. But here, what we're doing is taking this disk, is actually a washer that's doing this around the y-axis. Y is x equals -2 here. Okay. So that puts your outer radius here, your inner radius there, and you're subtracting the areas such pi r squared of those radii. However, here's the issue. You're taking a dy here, so you need to have your function as a function of y, not as a function of x. If you're taking dy's from 0 to 9, not dx's. If you're taking dx's, then there's another way to do this, but we haven't hit that yet. I think we'll do the same problem later. We're taking dy's here, so you need this in terms of y. So let's, in terms of y. So let's do that. Of course, okay. What we have is y is equal to 9 minus x squared. What we want is solve for x. So let's subtract, well, let's add x squared to both sides. There's a couple ways you could do this. I found it just about as easy to do it this way. And subtract y from both sides. And that gives you then x squared is equal to 9, minus y, and then you take a square root, x is equal to, and technically that would be plus or minus the square root of 9 minus y. But guess what? Your x's are always positive here, 0 to 3. So you don't need to do plus or minus, you just do the plus. And that's what they do here, 9 minus y, square root of 9 minus y. Okay? You're using the physical characteristics of the problem to help you identify the value. Okay? So there's your x. All right. Now the good news, well, no, not quite. If we weren't revolving this around, we're revolving it here, then that would just be 9 minus y squared, that'd be 9 minus y. That would be pretty easy. But we're revolving it around the line x equal -2, okay? That's going to complicate matters a little bit because it would be this value plus 2. And that's exactly what they show here. Square root of 9 minus y plus 2. And that's the outer radius. The inner radius is just the y-axis to here is 2 units. This minus that is 2. So that's going to be a pretty easy. Thing to do. Okay. So let's set up my integral. Yuck. All right. The integral is going from 0 to 9 because we're doing dy's here. Your outer outer radius is equal to the square root of 9 minus y. That's pretty ugly. Okay. 9 minus y plus 2. And then your inner radius is going to be minus 2 squared. Okay, so that's going to be it. All right, so the outer radius, the area of this part out here, around B here, that's going to be pi. Yuck, yuck, yuck. Pi. I'm sorry, if I write out here, it flips. No, I don't know. I don't know what it's doing. It's just doing weird things. Okay. Outer radius is the square root of 9 minus y plus 2 squared. Your inner radius is minus 2 squared is 4. dy. Okay? 2 squared. Okay. That would be pi times integral from 0 to 9. Now, square this binomial. What would you do? You get that in front, 9 minus y. because square of a square root is just 9 minus y. Plus 2 times, I'm going to write it in exponential notation, 9 minus y to the 1/2. You okay with that? Okay. Plus 4. Then we do a minus 4. They disappear. dy. All right. So it's going to be a pi. Boy. Not much you can do just except integrate. And what does that give you? Yeah. 9y minus y squared over 2. Oh, he had the okay. Let's do the integral of that, antiderivative of that. I'll put the plus 2. What will be out here? 9 minus y to the, no, you raise it by 1. 1/2 plus 1 would be 3/2. Then you would, second? Okay, I'm sorry. I can't hear. Oh, yeah, you're right. Okay. Except over 3/2, which is times 2/3, right? So it's times another 2 over 3. But then you've got one more thing, chain rule. So that puts a minus in front. Okay? So you see that? Oh, yuck. This thing is so aggravating. Oh. Sometimes it takes it and sometimes it doesn't. But it did it. No, it didn't. Okay, there it is. So I'll lose the, make that a minus. Okay? Now let's go back to the pen. Okay. And this is from 0 to 9. Now let's clean that up just a little bit before we, I don't know, the only thing you can do is make this a 4. Minus 4/3. That's about the only thing I can think of to do. Okay, so let's plug in our 9. Well, here we have a pi times 9 times 9 is 81. And this will be 81/2. And this thing keeps flopping on me, so this is so aggravating. Okay. Minus 81/2. That's the second term there. Minus 4/3 times, well, what's 9 minus 9? Oh my goodness. 0. That doesn't seem right, does it? At least to begin with, that's going to be a 0. So, it's so aggravating. Okay, so So that'll be a 0. Actually, I shouldn't have erased all that. Okay. But now you have to add the 0 in, or I mean subtract the 0 in. Well, what happens here, this becomes 0, that becomes 0, but this one is and it's a minus, so that's a minus plus 4/3 times 9 to the 3/2. Do you see that? Okay. Now, it'll be pi times, I'm going to go and write this as 81/2, because 81 minus 81/2 is 81/2. Okay, plus, now, what I suggest is that you take the square root first. The square root of 9 is 3. 3 cubed is 27. 3 will go into 27 9 times, and 4 times 9 is 36. Okay, which is 72/2. And 81/2 are 153/2. So pi 153 pi over 2. I hope that's it. No, it isn't. Yuck. I botched up something here. All right, let's see. Oh, man. Here's where I made the error. This is a 4 right there. I forgot to double it. So so that's going to be a 4. That's going to be an 8. That's going to be an 8. Okay. Let's see if we can get those corrected here. It's going to be a 4, because it's twice the cross product. And that would then be 2 to 8/3. Okay. This will be an 8/3. Alright. And that's the rest of that's the same. So this is going to be 3 cubed 27, 9, that's 72, which is 144 over 2 plus 81 over 2. And that's equal to 5 to 225 over 2 pi. And that's the answer they got. Sorry about that. You square this, that's a 4. Okay. Now, the math was, again, what was difficult. The calculus wasn't really all that bad, except integrating that. Interestingly, here, your upper limit goes to 0 and your lower limit gives you a value. Here, the upper limit goes to value and the lower limit gives you 0. So they kind of block out each other there. But this is using the washer method, okay, which is what we've been doing before, only this time we're revolving around on a vertical axis, so you have the y's in here. So this is the way you do that. But because you do dy, you have to get this as x in terms of y rather than y in terms of x. So that's the other step early on. Now, that I think finishes 6.3. I think this should probably, no. There is another slide. That slide comes from your summary here. Okay? These are, again, what we're doing is volumes of revolution. And these are just showing a variety of these volumes of revolution. different ways you can do it. Okay, first, we have a function here revolved around the x-axis. That's going to be a disk method. Since it's revolved around the x-axis, you take your dx, and the f of x is the radius that you're revolving, so pi times f of x squared dx. That's going to be all there is. The second one here is a difference in two functions, both of them positive, okay, about the x-axis, okay. So again, you take a dx here from a to b. It's the outer one squared minus the inner one squared. That will be the volume that's left, and you integrate that from a to b, and you've got it all. Okay. The next is going to revolve around some horizontal axis, not the x-axis. Okay? Now, when you do this, revolve around y is equal to c, that's up here above f. Now, your outer radius is your f, because they're revolving around the x-axis, and your inner radius is the g, so it's f squared minus g squared. Okay? Here, though, if that c is up above these, your outer radius is c minus g, whatever that g of x is, c minus g is the outer radius squared minus the inner radius squared, which is c minus f squared. Okay? You always take higher minus lower to give you the radius, but the outer becomes the one on bottom and not the one on top, because the c's up here. If the c were down here, then it would still be this one, but then you'd have a plus c at the end. Okay? F of x plus c minus a minus c. Okay? Whatever the sign is. Okay, so that's the third variation on the theme. And here's the fourth, and this is one I was just talking about. This time they didn't make c be negative, but made c positive, but still less than f or g. Then your radius is now, outer radius is f minus c squared. Your inner radius is g minus c squared. And pi times that. Yeah. Make sense? All right. They didn't show in the summary here the vertical, but yeah, they work the same way. Let's do some of these preliminary questions. Okay? And I forgot to open up, but I think it's actually better not to. Let's just go back. I'm sorry. Let me make sure. Yeah. Okay. I'm going to write on this sheet, even though it has nothing to do with this figure here. Okay. I'm just going to use the white page. Okay. Number one. Which of the following is a solid of revolution? A sphere. B, a pyramid. C, a cylinder. And D, a cube. Which of those is a solid of revolution? A sphere certainly is a solid in revolution. How about a pyramid? A cylinder would be. Pyramid and cube, they have angles in them. They're not rotating, so no, they can't be. So A and C should be our answer. This is 6.3. A and C. Got it. They got it right. Good for them. Okay. Number 2 here says true or false. Y'all both got your book, so I'm not going to write this. When the region under a single graph is rotated about the x-axis, the cross-sections of the solid perpendicular to the x-axis are circular discs. True or false? True. Yeah, that sure should be true. Let's see what they got. True. Good deal for them. Okay. Another one, true or false. When the region between two graphs is rotated about the x-axis, the cross-sections of the solid perpendicular to the this glare is in my eyes and I'm having trouble focusing on this. When the region between two graphs is rotated about the x-axis, the cross-section of the solid perpendicular to the x-axis are circular discs. Basically, same thing as before, except this is a region between two graphs. Are those discs still? Say again? They're washers. They're washers now, not discs. So that's false. Yeah, I think that's what you said. False. The cross sections are washers. And number 4. Which of the following integrals expresses the volume obtained by rotating the area between y is equal to f of x and y is equal to g of x over an interval a to b around the x-axis, and we'll assume the f of x is always greater than or equal to g of x is always greater than or equal to 0. Okay. I was trying to think what symbol that was, and I realized that's a closed bracket. Okay. All right. A here is the integral pi times the integral a to b f of x minus g of x squared dx, and the b part here is pi times the integral from a to b of f of x squared minus g of x squared dx. Okay, and you already said B, yeah, for sure. Okay, yeah. All right, homework exercises here. Do 1 or 3. Any of the odds 5 through 11. Do 13. Do any of the odds 15 through 19. Do either 21 or 23. Do 25. Do any of the odds 27 to 31. Do any of the odds 33 to 37. They have a hint for 36, but we're not doing that. Then do any of the odds 39 to 51. That's a big chunk of them. And then any of the odds 53 to 59. 53 to 59. All right, I was going to check here and see if there's something about a torus here. If there's something you want to write on that, you certainly can. And then there's something about hyperboloids. Those are just shapes. So I would. And then the ellipse fourth dimension too. We'll come closer to this later. Okay. Whew, goodness gracious. I can hardly breathe. How are we doing on time? 5 more minutes. Let's get started because I've already mentioned it. Let's just see what's next. Oh, I went upward to find the disk we could write on. Let's do 6.4. At least get started on it, if it'll come up. Yeah. Okay. Part of the reason maybe for my head being so clogged up too, I had a terrible night as far as sleep went. At 3 o'clock in the morning, our alarms went off. And it's our security system. They do something on Sunday evenings. And they haven't done it in a long time, but this time it set it off. They were quizzing the system, and they set it off. There was nothing inside that did it. It was right at 3. So I got up, I unplugged the battery, and went back to bed. At 3:30, it started again. So I don't know. I don't know why. Then I had to go down and disarm it, and that woke the dog up. So I went back to bed, and about starting around 4 to 4:30, sometime in there, she was scared. Well, I know what happened. The security company called the police because the alarm had gone off, but they're the ones who set it off, and then the police came by, but I slept through it. I didn't hear it, but they scared the dog, and she started barking. So she barked then from then until when I got up at 5:15. So basically, from 3 o'clock until 5:15, I had really spotty sleep, and that may have also contributed to the head. Sorry about that. You didn't need to hear all that. But anyway, let's, but just it dawned on me that's probably contributing to some of this. Okay. I have to go through all this to. One more. Okay. All right. Now, here is a second way to do some of the problems. I already alluded to it before. In addition to disks or washers, sometimes the setup of a problem gives it to a better way to do it. And I thought there was a slide before here, but this is the first one that popped up here, I think. The volume of a shell. All right. Now, I wish they had the picture with this, but anyway, let's picture this. If I go to write on it, it's going to shrink, but I think we've got to. Let's just sort of visualize this now. What we have is a graph here, three-dimensional graph, and we're going to take a shell of that graph. In fact, that one that we did the dy's on before, we're going to do the dx's this time. And a dx is going to define a shell that goes around the y-axis or something parallel, x equal -2, whatever it is, okay? And that shell, the volume of that shell that goes around there is going to be its radius, 2 pi r, that's the radius, times the height times the width, delta r. That's going to be the volume of any shell, okay? Now, if that radius has to do with the x-axis, that could be a delta x. If it had to do with the y-axis, that could be a delta y. So I sort of wish they didn't throw in that r there. But this r, capital R, is the radius from whatever the axis of rotation is to the point in question. That's the r here. So that's the bigger radius. H is the height of the shell, and dr or dx or dy, that's the thickness of the shell. Okay? there's the verbiage. They did start with this. I don't know why it skipped over it. Okay. I thought, why didn't they show the picture first and then, and they did show it first. It just skipped it. Okay. Now, here's what we were talking about. If you have this shell here, and we'll show why they're talking about the shell. It has an axis here that goes through this point here. Now, you have your outer radius is what they call it capital R. The inner radius they call it little r. And then delta R is that thickness, okay? The thickness of the shell. The circumference of the shell is 2 pi times the bigger radius. And the height is that. So that gives you the volume of that cylindrical shell. And again, I don't know why they're using the R's in this way. But the delta R here is your capital R minus your little r. In the limit, that's just going to be an X or a Y or something like that. So that's your radius around the curvature. This is the change of that radius, which could be an X or Y, whatever they call it, R. All right, so there was the formula. Now here's why they do these. Okay. All right. Let's say that we have a curve here, y is equal to f of x. We're going to rotate this around the y-axis. Okay? Is it time? It is. Okay. We'll pick up there next time. This is going to be pencil. We'll pick up with this graph right here next time. No new homework exercises there. We'll pick up with this there. All right. Now remember, I'm beginning to think that this was so wet earlier. I was thinking I was going to go home and think I may stay the afternoon unless this gets itchy or something like this, because I have sugary stuff that's spilled on my shirt and pants. But so far they don't look too bad, and I think I can live with them. So I may stay the afternoon after all. Good deal. We'll see you on Wednesday.